In this lesson, we're going to study about exponential functions. The function that I have written here would be just your parent function, your basic function of an exponential. The b is just representing a number, and that is referred to as the base. But when you look at a function, the way you know that it's an exponential function is the fact that your variable is in your exponent. That's the sign for sure that you're dealing with an exponential function. All right, you do have one special type of exponential function that's called your natural exponential function, and that is specifically when your base is e. Now, e is a number. It's kind of like pi. It doesn't look like a number, but it is. It is irrational, which means just like pi, it just the decimal places just keep going and going and going. They don't repeat, and they don't terminate. And e is approximately 2.72. Just like we know that pi is about 3.14. All right. So what we're going to do is look at graphing a few exponential functions. So the first one that we're going to graph is going to be y equal 3 to the x. And as it says, we're just going to use a table of values to do this. So in setting up your table of values, now you can choose whatever values you want to for x, because you can substitute anything that you want to, any real number, in for your exponent here, your x. But you don't want your numbers to get too large when you go to graph these, because you don't want to have to, put tick marks out to 27 units or something like that. So I'm going to go with positive 2, positive 1, 0, negative 1, and negative 2. And use those. I'm just going to use those each time that we go to graph an exponential. All right, so substituting those in for x. Of course, first of all, you'd have 3 to the second power, which is 9. 3 to the first power, which gives us 3. 3 to the 0, which gives us 1. 3 to the negative 1. Now, just a reminder here about your negative exponents. If you want to rewrite it so that you have a positive exponent, remember you have to bring it to your denominator. So like 3 to the negative 1 is just the same thing as 1/3. So then 3 to the negative 2, that means if you rewrite it and bring it to your denominator, of course that ends up giving you 1/9. Okay, now taking these and graphing them. Okay, so plotting the point 2, 9, 1, 3, 0, 1, negative 1, 1/3, and negative 2, 1/9. Now, an exponential function, as I said earlier, you can substitute whatever you want to in for x, which means your domain is negative infinity to positive infinity, which would indicate that you do put arrows at each end. It does keep going. Now let me explain about what happens right here. As this graph comes down, and as it's just going to gradually get closer and closer and closer to your x-axis, but it's not ever actually going to touch it, so obviously it does not even go across it. You have a horizontal asymptote at your x-axis, so you've got to make sure that you level your graph off and don't drop it below that x-axis. Okay, so looking at another one, we have y equal 2/3 to the x. So again, we're going to do this by setting up a table. And I'm going to use the same x values that I did just a minute ago. Okay, so 2/3 to the second power would give me 4/9. 2/3 to the first power is 2/3. Then we'd have 2/3 to the 0, which is 1. Now you can go through and do the same thing that I did a while ago with the negative exponents, but here's just like a little shortcut. The y values that you have for these two will always be the reciprocal of these two, and that's just a quick way to fill your table in. So we're +1, x equal +1 gave me 2/3. The -1 is going to give me 3/2, because that negative exponent is going to cause everything to, like if it's on the top, you take it to the bottom. If it's on the bottom, you take it to the top. So it just ends up being the reciprocal. Then -2 would then be the reciprocal of the 4/9, so we have 9/4. Okay, so graphing this one. Okay, now as far as the fractions there, I mean, obviously when you go to plot these points, you'll want to do a decimal approximation. So like when you plot the point 2 and 4/9, 4/9 is just a repeating 4. So it'd be pretty close to halfway right here. And then 1 2/3. And then 0 1. -1 3/2. Of course, the same thing as 1 1/2. Now 9/4 is 2.25, but I mean, if you round it, it's approximately 2.3. It's going to be about the best we can do on just estimating. Okay, so now connecting this up. Now keep in mind, as it comes down, it gradually gets closer and closer and closer to your x-axis, but it's not going to, like I said, touch it or for sure even go across it. So this one's not quite as steep as the one that I drew a while ago. That's just going to vary depending on what your base is. But it's also going the opposite direction. Like a while ago, the one I had was going up on the right, and it leveled off along the x-axis as it came out to the left, and this is doing right the opposite. And again, which way it turns is going to be determined by the base. So just remember, again, you do have a horizontal asymptote here at the x-axis. Okay, one more that we're going to graph is y equal e to the x. So we're going to graph the natural exponential. Okay, again, doing your table. Now with these values, because e is an irrational number, you'll just have to enter these in your calculator. So like e to the 2nd power, if I round it to 1 decimal place, that's approximately 7.4. E to the 1st power will be about 2.7. E to the 0 is 1. Okay, and then we need to calculate e to the -1. That's going to be approximately 0.4. And then e to the -2 will be approximately 0.1. Okay. Okay, so 2 and then 7.4, 1, 2.7, 0, 1, -1.4, -2.1. Now this one turns the same direction as the very first one I did. But if you remember, the very first one that I graphed had a base of 3. And if you think about it, e is about 2.7. So you don't have a big difference there as far as the value of the base from my first example to this example. So that's why those two graphs are real similar to each other.